Welcome back to the course. In this video, we will take a look at the status quo of the circular bioeconomy. Traditionally, system engineering and modeling have predominantly focused on substituting fossil fuels with renewable energy and biomass and enhancing efficiency within constrained system boundaries. There is an urgent need to broaden these systems' boundaries to include both technological and ecological recycling. Existing and emerging circular bioeconomy practices can serve as a prime example of system integration. These practices facilitate the interconnection of complex biomass supply chain networks with other networks encompassing feedstock-independent renewable power, hydrogen, CO2, water, and other biotic and abiotic resources. The illustration in the following figure advances the state-of-the-art by including aspects of the economic metabolism that are underrepresented in Sankey graph found in the literature and provide a combined graph of energy, material, and food flow which is necessary to capture the potential extent of the circular bioeconomy. The figures show the status quo of the circular bioeconomy and its coupled sectors by merging available Sankey graph data into a novel representation of economy-wide resource flow between the biosphere and technosphere. The first figure shows the EU27 resource flows in 2017 based on mass content. Electricity distribution and use cannot be meaningfully related to mass flow but are still included as one-dimensional lines to indicate the relevance based on energy content. In the next figure, we can see the EU27 resource flows for 2070 based on energy content. Errors and emission cannot be meaningfully illustrated in energy flows but are still shown as one-dimensional lines to indicate their relevance based on mass content. The integration of segregated energy, material, and biomass flow assessments brought the advancement of the current state of the art in the following ways. First, a shift in focus towards fundamental social requirements or the fundamental rationale underpinning the preservation of resource streams. Second, the inclusion of mechanisms for quantifying resources that are either circulated within the system or dissipated as waste. Third, the depiction of resource flows in accordance with their distinct functional units, thus affording a more granular and nuanced representation of the data. The outcomes of this analysis define the current limitations with regard to our capacity to depict a resource stream that may come under the purview of the circular bioeconomy and multi-sector integration in the forthcoming decades. These long-term alterations in the resource flows can be divided into four primary categories. 1. Substitution, using alternative resources to achieve the same outcome. 2. Efficiency, achieving more with less, such as reducing waste or making better use of resources. 3. Sufficiency, rethinking what is necessary by questioning the urgency of resource consumption and considering non-consumptive options. 4. Reliability, creating processes that do not fall, often achieved through integrating systems to distribute surplus resources to cover shortages. In this video, we learned about the status quo of the circular bioeconomy, Sankey graph data, and long-term alternation in the resource flows. We have arrived at the end of this video. Thank you for watching, and I'll see you in the next unit.